In the recent years, the Internet of Things is undergoing a relentless growth, enabling a plethora of new applications around us, such as Industry 4.0, unmanned drone deliveries, virtual reality, and remote surgery. This growth has been followed by an evolution of infrastructure architectures which are becoming more and more pervasive and heterogeneous, embedding thousands of nodes along the continuum from the IoT to the cloud. Naturally, such large-scale infrastructures suffers from node failures or overloading, traffic congestion, and disconnections of their nodes. On the other hand, software applications are also becoming more complex systems, being made of hundreds of interacting microservices, which must meet their stringent end-to-end QoS requirements on latency, bandwidth, security, just to name a few. Hence, application management should continuously decide where to place services, both at first deployment of an application and every time node failures, overloading, congestions, disconnections forbid meeting application requirements as a whole. The key idea of continuous reasoning is to exploit compositionality to differentially analyze a large-scale system by mainly focusing on the latest changes introduced in the system and by reusing results of previously computed analysis as much as possible. This idea has shown very successful in supporting iterative software development at large-scale IT companies. Indeed, incremental static analysis enabled by continuous reasoning permit to verify properties of every code modification and to identify bugs that can lead to crashes or poor performance as soon as they're introduced in a codebase. This is precisely the case of Facebook's Infer. Starting from this idea, we propose a novel declarative methodology in its open source prototype, FogBrain, that makes informed service migration decisions when infrastructure variations prevent running applications from meeting their hardware, software, IoT, or network requirements at runtime. Our methodology shows three main elements of novelty corresponding to very desirable properties for cloud IoT application management support. FogBrain is declarative, more concise, easier to understand, modify, and maintain when compared to existing procedural solutions. And it is also characterized by a high level of flexibility and extensibility which suits the ever-changing needs of cloud IoT scenarios. It is intrinsically explainable as it derives proofs for input user queries by relying on Prolog state-of-the-art resolution engines, and it can be easily extended to justify why a certain management decision was taken at runtime in the spirit of explainable AI. Finally, it features scalability by supporting application management at the large scale by relying on a continuous reasoning approach to reduce the size of the considered problem instance only to those application services currently in need of our attention. And last but not least, FogBrain is open source. You can find it online with live documentation.
FogBrain implements two different types of reasoning. So the first one is for the first deployment, when we need to first deploy the application on the continuous infrastructure, and this is implemented with a generate and test strategy, as you see in the Prolog definition below in blue. The other part of the reasoning is perhaps the more interesting part is the continuous reasoning that is implemented by FogBrain in order to implement management decisions, which means to migrate services from one node to another, as we will see. FogBrain determines the first deployment of an application over a continuous infrastructure by exploiting generate and test with backtracking. What FogBrain does is checks for each service S the software, IoT, and hardware requirements, and it checks whether these hold in order to place service S on a node N. If this holds, then it checks latency and bandwidth requirements with respect to all the other services that communicate with S and that have been already placed by FogBrain. And this is repeated until all services have been successfully placed. The other part of the reasoning implemented by FogBrain is the continuous reasoning part. FogBrain identifies the services to be migrated due to two problems that may occur. So one are problems with the deployment node, which means that the node N on which service S has been deployed is not capable anymore of supporting that service. And the other type of problem are communication problems that may occur among services. This is defined by the two predicates that you see below, the on-suffering node, which relies on the definition of this node problem predicate, and on the suffering link, on-suffering link, which relies on the definition of the communication problem predicate. Here we see FogBrain at work with our reference example. So we see that we can invoke FogBrain with the VR application in order to find a suitable placement B. And for the first deployment, FogBrain determines that the VR driver service should be placed on the access point node, the scene selector on the cabinet server, and the video storage on the cloud. And this is what we see here with the green boxes. Now, what is interesting is that at some point, the video storage service has a problem, whether it is a node problem or a communication problem. FogBrain detects that the video storage needs to be migrated, and after that, it builds a partially ground query to determine the new placement for migrating only that service, as shown in the blue rectangle below. So this way, FogBrain determines a new placement that, as you see in green, it detects the new placement for the problematic service.
Overall, FogBrain represents the core of a continuous reasoner to support cloud IoT application management. It is declarative, explainable, and scalable, and it achieves considerable speed up with respect to non-incremental reasoning solutions. Besides being declarative, it is concise, only 125 lines of code, and easier to understand and extend so to account for new emerging needs compared to existing procedural solutions.
Good morning, welcome to my presentation. Since when do us humans fancy to reproduce other intelligent beings? Since a long time, but together with the dream there is the fear to create a bad robot that would overcome the humans. In fact, in the Star Wars movie, droids were equipped with what was called a restraining bolt, which the user could regulate so that the behavior of the droid would be according to her expectations. But how to implement such a restraining bolt? Because intelligent agents are often autonomous. They interact with humans with an environment in an unpredictable ways. Now, since an agent is a piece of software, it can be verified prior to deployment. But still, via learning and interaction with the environment and with other agents, an agent can develop behaviors and objectives not in line with the user's intentions. So, either there is always a human in the loop to check the behavior of agents, or if agents are really autonomous, they should be able to correct themselves. Since many decades, some researchers have treated the issue of self-aware and self-expressive computing, where a system would be able not only to observe the environment, but to observe its own memory, reasoning, learning devices, and have an awareness of its own behavior. Uh, and this view led to the fact that at the meta level, one could define properties of control in the same way as at the object level you define properties of the domain. So agents should reflect of themselves so as to block inappropriate behavior, but also, if possible, to lead to self-modification and self-improvement of appropriate behavior. We can have two kinds of reflection mechanisms, either local, operating on single actions, or global at a higher level, the level of objectives, desires, plans, and so on. Such mechanisms could be based on reflexive meta-reasoning. This is an example of local reflection mechanisms. These two distinguished predicates, solve and solve not, defined at the meta level, they capture the intention of an action to execute an action, the intention of the agent to execute an action, and they check if the action is ethical in the present context. For instance, killing someone could be ethical in a video game, but certainly not in reality, and thus it could be allowed, or if it should be disallowed, either because not ethical in the present context in general, or because, as shown here, because it is an ethical exception. For instance, killing someone is ethical in general in a video game, but not in a video game intended for children. This is instead an example of our global reflection mechanisms. Assume that an agent has a critical resource R, and that the agent does not want that the quantity V of R gas below a threshold. Then the designer can set a constraint that indeed the quantity should never go below the threshold, and this n is never in LTL, in linear temporal logics. The expression also says that a certain number of supply events will have happened in the past, so replenishing the quantity of resource, and a certain unpredictable number of consumption actions, each for a quantity Q, are expected to happen, but in any case, if the quantity of R gas below the threshold, the repair action is after the div here, and is to block consumption of the resource. Such expressions are automatically checked at a certain frequency or upon occurrence of certain events. Clearly, you can have several expressions to check various aspects of the agent's operation. We have prototypically implemented these that we call AILTL expressions, both in Prolog and in DELI, where DELI is the agent-oriented logic programming language that I invented years ago and is developed by my research group and is equipped with reactive and proactive features. Experiments have shown that DELI outperforms Prolog whenever we have big events dataset, and the overhead for checking the single expression is sustainable Clearly, there can be potential scalability problems if there are too many expressions to check, and so a designer should find a compromise, a balance between accuracy and efficiency. So, thank you for your attention on my behalf and on the behalf of the good robots that we will certainly design in Delhi.
Hello and thank you for being here. I'm Bozzato from Fondazione Bruno Kessler and I'm here to present the paper towards distributed contextualized knowledge repositories for analysis of large-scale knowledge graphs, a joint work with Christoph Schuetz from University of Linz. In this work, we extend our proposal for all-up analysis of knowledge graphs towards a distributed version of our framework in order to deal with large-scale and distributed knowledge graphs. In our previous work, we introduced the KG-OLAP cube model, a multidimensional model for analysis of knowledge graph information based on contextualized knowledge graphs, and in particular formalized as an application of the CKR framework. Knowledge in KG-OLAP is organized in cells that are characterized by hierarchically organized dimensional values. This organization allows for the definition of OLAP-like operations on cubes for the analysis of KG information. A problem in this organization stands in the centralized view of the model. This is not applicable when information is distributed across different repositories, and moreover, experiments have shown that it is impractical in case of large knowledge graphs or large number of cube cells. Thus, in this work, we provide a first definition for an extension of the KG-OLAP model to distributed knowledge graphs, and we show how the OLAP operation can be extended in the case of the distributed model. I'll introduce the model by means of examples in the scenario of messages in the air traffic management, which is our use case of interest. In the case of the KG-OLAP cube, we organize the knowledge by defining the hierarchy of dimensions that characterize the cube cells. In the air traffic management scenario, for example, we can consider the time, topic, and importance of messages relative to an airport. Using these three dimensions, we can then visualize like this the organization of knowledge in cells in the three-dimensional cube. For example, this can represent the organization of messages relative to the repository of LOWW, that is the Vienna airport. We can also visualize the cells as organized in a hierarchical structure defined by their cube dimensions. For example, we say that the information relative to 2020 in all topics and importance are more general than the ones for specific months or topics. The organization also provides a way to define a notion of propagation of knowledge. We want that more general knowledge and axioms propagate to the more specific cells. Formally, this is represented in a contextualized knowledge repository composed by a global context that contains the structure of cells and global knowledge, and a set of local knowledge modules associated to the local cells. Now we want to distribute this structure. The idea is that we have a hierarchical organization of nodes to which we associate a local cube that represented the local information. For example, here we see that we have a general cube for all European airports, two different repositories for the Austrian area, and a more specific cube for the Vienna airport. With respect to the knowledge propagation, we define this model so that the knowledge propagates not only across the cells in the same cube, but also from the more general to the more specific counterparts of the same cell across different nodes. This is formalized by extending the CKR framework to a distributed version. Basically, we have a local CKR for each node, and to each of them we add a set containing the direct relation with the higher and lower nodes in the hierarchy. Over this definition of distributed KG-OLAP cubes, we can define our OLAP operation, in particular the contextual operation that modify the structure of cells can be now defined along the node structure and the cell structure. So in the following, I can show you the two variants of the slice and dice and merge operations. On the other hand, graph operations that modify the contents inside the single cells can be defined similarly to kg-OLAP cubes. Node slice and dice filters out one node and its connected nodes. For example, here we can see the effect of the operation to the LOVV repository. Similarly, but applied to cells, the local slice and dice selects cells on the base of their dimensions. If we only consider the time dimension, this is the effect of selecting cells on the base of a specific mount. The merge operations take knowledge from finer granularities and merge it to the higher granularities. In the case of node union merge, knowledge from repositories in the lower levels is rolled up to the nodes in the higher position. For example, here we see the effect of merging the knowledge in the node for Europe. The knowledge is merged in the respective cells of the higher node. Similarly for the local merge but applied to cells. The abstraction is defined by a level in the dimensional values, and cells in the lower levels are merged to the higher cells. Here we show an example of a one-dimensional structure with time, where we apply the roll-up to the year level. In conclusion, in this work we proposed a first extension of the KG-OLAP model towards distributed cloudless graphs, and we have shown how the OLAP operation can be extended to this structure. We are currently working for extending the reasoning methods and implementation of KG-OLAP to the distributed case, and we also want to evaluate the model possibly on real data from the air traffic management scenario to understand the advantages and limits of this model with respect to the centralized model. So that's it from my side, and thank you for your attention.
Good morning, I am Matteo, and today I will be talking about mutation analysis and COC. So let's immediately get started. One of the biggest problems of formal verification is that yes, it gives us the highest possible assurance of correctness, but at the same time it is a time-consuming and labor-intensive activity, as we all know. Validation or testing is usually cheaper, in the sense that we can automate part of the process of testing, but it is usually not as reliable as formal verification. One could wonder, what is the point after all of performing testing in proof assistant? I mean, we could write proofs and be fine with it. The truth is that sometimes we don't know if a given theorem is true or false. And if we discover early that a theorem that we are trying to prove is false, then we don't have to spend time proving something false, basically. And in this talk we will show how mutation analysis and property-based testing can cooperate to perform validation in the domain of the semantics of programming languages. The core idea behind mutation analysis is actually quite simple. Let's suppose we have a program and a test suite for our program. How can we know how good our test suite is? With mutation analysis, we basically produce a lot of mutants, which are copies of our original program, but with slight modifications in it, induced by a so-called mutant operator. If our test suite is able to spot these differences, is able to spot the bugs we introduced in these mutants, then we say that the mutants are killed. Otherwise, we say that the mutants remain alive. And the ratio between the alive and killed mutants is an indication, rough estimate of how good our test suite is. So we decided to perform mutation analysis on PBT suites. PBT stands for property-based testing, and it is basically a testing technique in which we try to falsify a given property by means of a randomly generated data test. The core idea during this talk will be, okay, given a model of a language, let's inject faults in it, and through PBT let's try to see if our testing suite are able to spot these faults we just introduced. And here MutantCheck comes in our aid. MutantCheck is a small library that we developed for the proof assistant COC. It heavily relies on MetaCoc, which is a metaprogramming library for this proof assistant. Mutant-check provides a set of built-in mutant operators, but also a DSL to define custom operators. One interesting fact about mutant-check is that default mutant operators are guaranteed to be type-safe. That means that we can reduce the number of mutants that are generated, and in this way you can somehow deal with the problem of combinatorial explosion. We don't solve the problem, but in a way we can deal with it with this approach. So here is an example of mutant-check in use. So here we see the expression we're going to mutate, so 4 times 5. We mutate it using this operator in which multiplication becomes addition, and we name whatever comes out from this mutation mul2add. When we print mul2add, we get exactly what we expected, so 4 plus 5. It's important to notice that this operator is possible because both mul and add have the same type signature. Otherwise, the type checker of Coq would complain. So the process is really simple actually. We have this expression 4 times 5, which is reified using embedding it into these strange parentheses. And we get this AST representation of our original expression. We then apply an AST manipulation in which multiplication becomes addition, and here we see the result. And we then get exactly what we expect, so 4 plus 5. Here is a list of the built-in operators for mutant-check. I will not get too much into details about them, but we have just seen substitute, the arrow we have just seen, and we will use in a moment a swap, which exchange the order of two terms in a given expression, and if we want a meta operator on constructors, which takes an operator, a simple operator, as an argument and applies it to every constructor of an inductive type. Now, for a slightly more complex example, we will consider a toy arithmetic language taken from Peirce's software foundation, and we will apply some mutation and see if our PVT test suite is able to spot these mutations. I didn't mention it before, but we are going to use QuickCheck, which is de facto the standard property-based testing library for Coq. Okay, and here are the typing rules. I will not discuss them in details. I will focus more on the last one, which is the one we are going to mutate. So the last one says that if t1 is a natural number, then the function call is 0, t1 is a Boolean. And this is the corresponding Coq code. We are going to mutate it by exchanging the order of these two types. So if t1 is a Boolean, we say that is0 t1 is a natural number, which is of course wrong. This is the corresponding code. How do we do that? Well, we simply use the same DSL we used before. So we mutate as type, so the definition in Coq which embeds the typing rule, using on every constructor the operator swap the type of natural with the type of bool. And we name whatever comes out of it as type mut. Now we need a property to test, and we choose to test progress. Progress means that if we have a well-typed term t, then either t is a value, so it is irreducible, or t has a t first to which it can be reduced. So we quick check our progress property and we see that we can find a counterexample. So our mutant is killed and our PVT test suite can survive another day. As a conclusion, validation is a useful tool to reduce proving time, and we've seen that the couple mutation analysis and property-based testing is a good one, and they can cooperate to perform validation successfully. We plan to, in the future, to optimize further mutant-check, both on a computational level, so we'd like to speed up a little bit the computations, and also on an ergonomic level, so we would like the user to write less boilerplate code as possible. Thanks for watching.
Hello everybody, my name is Giovanni Sileno and I'm a researcher from the University of Amsterdam. I will now present joint work with Matteo Pascucci from the Slovak Academy of Sciences. So everybody can see that we are passing from a paradigm of individual computing devices towards distributed forms of computation. And this means that we are passing from mechanical to institutional approaches to computation. We are not concerned anymore just by instructions, but also about contracts, regulations, and laws that applies on the computational system. The contribution of the paper is a language that captures Offel's framework of normative position. The language is a language of multimodal logic with alectic operators with respect to simultaneous nodes, temporal operators with respect to successive nodes, and deontic operators, and involve no form of quantification. Now, there are three main families of normative specifications in computational settings. The first one is the one used in control models, here exemplified by an Apache Web Server configuration. Typically, a user may have or may not have the permission to perform certain actions in the system, like reading or writing. The second family stems from the tradition of deontic logic. Deontic logic is illustrated on the square opposition, showing that obligation implies permission and the negation of permission is prohibition. The third family is associated to the framework of normative concept given by Offeld 100 years ago. Offeld made clear two important points. First of all, when there is a duty, there is another party which has a claim with respect to that duty. And second, if there is a duty, that means that someone at a certain point in time, had the power to create the duty, and the person that is now the duty holder was liable to that power. So Offeld, with respect to the previous two families, introduced this fundamental concept, which is power or ability. Now, if we look in the analytical literature, the concept of ability has been researched by several authors, and they presented definition as, for instance, like the possibility of an agent X to bring about a situation phi, or in the STIT tradition, the possibility of an agent X to deliberatively cease to it that phi is the case. But again, in this contribution, the focus is on situations. While if we look in other disciplines like psychology with the concept of affordance, in robotics, or even in event calculus, the focus is primarily on actions that determine change. So there is an analytical gap with respect to ability, and that's actually our starting point. So we propose a minimal language with the two basic predicates, like the agent X performs a certain action alpha, the object Z is in a configuration S, then there are a Boolean formulas constructed with Boolean operators and with two modal operators. So in all simultaneous alternative nodes, phi is the case, and in all successive alternative nodes, phi is the case. Now, we consider a special object star for the whole system. By doing so, we can associate configuration of the whole system with the propositional formulas that describe them. So here, that means that the whole is in a configuration as phi if phi is the case. By using these components, we can define ability as directed change. So the agent X has the ability, by performing alpha, to obtain the configuration of the whole phi if it is possible for the agent to perform the action. The target outcome is not present in all successive nodes, and in all simultaneous alternative, if the agent performs the action and the target outcome is not present, then the target outcome is present in all successive nodes. We can highlight here two properties. The first one is counterfactuality, and the second one is sufficiency of action to create the target outcome. In the paper, we define similarly negative ability, that means the ability of inhibiting a certain outcome, and disability as the absence of positive and negative ability. We extend the language by by means of deontic operators, specifically one associated to directed obligation. So X or Y phi means that phi is obligatory for X, and X is the duty holder with respect to Y, and Y is the claim holder. The paper presents an axiomatic calculus, and we prove that it is sound and complete with respect to its standard models. Now, let's return to the Offeld original framework. So, according to Offeld, the duty is about an action, and that's from one agent X towards another party Y. So we can define that as the obligation of X towards Y that X performs the action alpha. Similarly, we can define power of X towards Y of obtaining a duty of reaching phi by performing alpha as the ability of X to create the obligation upon Y of reaching phi by performing alpha. Now, the original definition of duty was primarily about action, and again, actions performed by the duty holder, while the power was mainly primarily about creating obligation. We're extending this concept by considering any formula, so that means a duty about reaching a certain state or an action performed by other actors, and also with respect to power, any conjunction of normative position as an outcome. Let's consider example of use of this framework. So a sale contract, we can write it as the power from a seller to offer, and by means of offering to create the power from the buyer that by accepting creates two duties: the duties of the buyer to pay and the duty for the seller to deliver. Another example comes from the data protection context. So typically a data controller is prohibited to process the data with respect to the data subject, but he has also the power, by collecting consent, to release the duty, so to gain a privilege with respect to the data subject to process the data. Finally, an example that doesn't consider any deontic concept: exclusive delegation. So let's imagine that the agent X has a certain power, but he has also the power, by delegating, to create the same power for an agent Y and remove the same power for him. So this kind of structure cannot be represented by using merely deontic concept. So we reach the conclusion. The paper reports on a research effort that unify insights from modal logic and normative systems. The key message is that there is a deep entrenchment between deontic and potestative categories, and that the second one are required to model complex coordination mechanism, like, for instance, delegation. In future developments, we want to investigate enforcement mechanism, the relation of power with conditional obligations, and the introduction of objects, agent roles, and more complex forms of refined actions. Thank you very much for your attention.
Hello everyone. Let me first clarify the terminology used in this presentation. Constraint-horn clauses is just another name for constraint logic programs, which is now standard in the field of program verification. Constraint-horn clauses are indeed becoming very popular in program verification because they allow straightforward encodings of verification problems. For instance, a partial correctness property specified by Hoare triple can be translated into verification conditions written as constraint-horn clauses, such that the Hoare triple is valid if and only if the clauses are satisfiable. Then, by using a constraint-horn clause solver, we can try to show the satisfiability of the clauses by computing a model that is a substitution of constraints for predicates that makes all implications true. In this work, we apply the constraint-horn clause verification approach to functional programs computing on ADTs, such as lists and trees. For instance, consider a recursive program implementing the insertion sort algorithm. One property that we may be interested in proving is that the multiset of elements of the input list is preserved by the sort function. Thus, we define a count function that counts the number of occurrences of a given element, and we want to prove that for all lists L and integers x, count of xl is equal to count of x sort of L. Following our approach, we translate this property into constraint-horn clauses. The clauses are satisfiable, but no model is expressible in the constraint theory, which is the union of the quantifier-free theory of lists and linear integer arithmetic. Thus, state-of-the-art constraint-horn clause solvers cannot compute any model and cannot prove satisfiability. An approach that has been followed for overcoming this difficulty is to extend solvers with induction proof rules, so as to be able to prove properties with universally quantified ADTs. An alternative approach that we follow in this work is to transform a set S of constraint-horn clauses on ADTs into a new set S prime, such that S prime is on basic types only, that is integers or booleans, and the transformation is sound, that is, if S prime is satisfiable, then S is satisfiable. Indeed, the soundness of the transformation is guaranteed by the use of the unfold transformation rules. The main advantage of the second approach is that we need not extend the constraint on closed solvers. We have designed a transformation algorithm called ADT removal, whose details can be found in the paper. In the insertion sort example, by applying this algorithm, we get a set of clauses with new predicates defined on integers only. No more lists terms are present. This final set of clauses is satisfiable, and indeed Eldarica is able to compute a model expressible in linear integer arithmetic. And thus, by the soundness of the transformation, the property we wanted to prove indeed holds. The ADT algorithm also introduces some new special predicates, which we call difference predicates. By matching the predicate definition that encodes the property to be verified against the predicate definitions derived by unfolding. Difference predicates correspond to lemmas in a proof by structural induction. We have implemented our technique on a tool called ADT-REM. We rely on a translator for constraint on clauses from SMT-lib format to Prolog syntax. Then we apply ADT removal to clauses in Prolog syntax, and we translate back to SMT-lib. Finally, we apply a constraint on clause solver, which is either Eldarica or Z3 with the spacer engine. Here are the results of our experimental evaluation. Our benchmark is a set of 169 satisfiability problems taken from benchmarks of other tools, either theorem provers or verifiers. The problems require the verification of universally quantified properties of recursive functions on ADTs such as lists, trees, queues, and heaps. First, we have run Eldarica and Z3 on this benchmark before transformation, and as expected for this type of problems, the results are quite poor. Then we have applied ADT removal. The algorithm terminates on 129 problems out of 169, and after ADT removal, the number of problems solved by the CHC solvers is much higher. Our results also compare favorably with a tool which extends the SMT solver CVC4 with induction. To wrap up, we have seen that constraint on closed transformations can aid verifying programs that compute on ADTs. We have shown through our experimental evaluation that ADT removal substantially improves state-of-the-art constraint on closed solvers, and also that ADT removal followed by the application of solvers is competitive with the extensions of solvers by using induction. The advantage of the transformation-based approach is that we can separate inductive reasoning from constraint on closed solving. One limitation of our approach is that ADT removal may not terminate on some verification problems, and it would be interesting to identify classes of problems and sufficient conditions for termination. Thanks, I'm ready to take questions.
Hello everybody, I'm Gianluca Bozzato, and in this talk I will present a joint work with Marianna Girlando, Bjorn Lellman, Nicola Olivetti and Stefano Pesce about theorem proving for conditional logics. Conditional logics are extensions of classical propositional logics by means of a conditional operator, allowing to have formulas of the form A conditional operator B. They can be seen as a sort of generalization of multimodal logics, where the modality is indexed by formulas of the same language. Conditional logics have a long history, and recently they have found several applications in different areas of AI and knowledge representation. In spite of their significance, very few proof systems have been proposed for conditional logics. In this work, we focus on some conditional logics of the Lewis family for counterfactual reasoning, where a conditional, A conditional B, is interpreted as if A were the case, then B would have been the case, where the antecedent A is false. And in this work I will try to outline the main features of TwoClever, a theorem prover implementing in Prolog some hypersequent calculi recently introduced for the strongest logics of this family, namely those admitting the properties known as uniformity and total reflexivity. Following the formulation provided by Lewis, we take as primitive a further operator, a comparative plausibility operator, with a formula A operator B, meaning A is at least as plausible as B. Lewis counterfactual A conditional B is then defined in terms of such a comparative plausibility operator. Lewis logics have a sphere semantics. A model is a triple, where W is a set of worlds. SP is a function mapping each world W to a set of spheres, namely a set of worlds, alpha, beta, and so on, that intuitively are close to W. They are spheres of worlds satisfying the properties that I've shown in this slide. For instance, they are nested. Given two spheres, alpha and beta, of W, either alpha is included in beta or vice versa. We also assume, in particular, the properties, as mentioned, known as uniformity and total reflexivity. A model also contains a valuation function assigning to each propositional variable the set of worlds where it holds. The valuation function is extended as usual to complex formulas. In particular, for a formula built from the comparative plausibility operator, we have that A comparative plausibility B holds in a world W if for each sphere alpha of W, if alpha contains a B world, then it has also to contain an A world. You can also see the evaluation of a conditional formula. The basic logic VTU is the set of formulas valid in all spheres models. As in modal logics, we obtain extensions of the basic system by assuming specific properties on the models. We have considered the three conditions proposed by Lewis in his seminal work: weak centering, centering, and absoluteness. These are the logics of the Lewis family, obtained by combining the conditions of the previous slide. These are the ones that we have considered in this work. You can see also weaker logics, the basic system V and its extensions, not assuming uniformity and total reflexivity, that we have already considered in previous works by also providing a theorem prover called Vinte. Our theorem prover TwoClever implements some hypersequent calculi recently introduced. In order to have an internal calculus, namely we want a calculus where every configuration manipulated by the calculi have a direct translation into a formula of the conditional language, we need some specific objects. We have conditional blocks and transfer blocks. As usual, a sequent that we call extended sequent, containing also these special objects, is a pair, gamma proof delta, where gamma is a finite multiset of formulas and delta is a finite multiset of formulas, conditional blocks, and transfer blocks. An hypersequent is a finite set of extended sequents. So these are the rules of the calculi. Obviously, I have not enough time to provide details. As usual, in order to check the validity of a formula, we try to build a derivation, that is to say a tree having such a formula as the root, and the tree is built by applying backwards the rules, and we have a derivation when all the branches are closed, that is to say that their leaves are instances of the axioms. We have implemented the hypersequent calculi in Prolog. We have followed the basic ideas of the Lee methodology, namely to implement each axiom or rule of the calculi with a Prolog clause. The proof search is provided for free by the depth-first search mechanism of Prolog without any additional ad hoc strategy. We then obtain a decision procedure by simply avoiding the redundant application of the rules. The resulting code is extremely compact. We have a main predicate proof which succeeds if and only if the hypersequent is derivable, and in this case the second argument matches a representation of the derivation, the clause 3 found by the prover. This is the clause implementing the rule taking care of the comparative plausibility operator on the right hand side of the sequent. So this is the interface. For instance, if you want to check whether this formula is valid in a given system, for instance the basic VTU, you just have to type it in the text box and then to click this button, and the answer is that the formula is valid. The proof tree built as a PDF file. We have also tested ToClever. In particular, we have compared its performances with those of Vinte on formulas provable on both systems, and the performance of ToClever seemed to be promising. In future works, we aim at extending ToClever in order to compute a counter model in case of a failed proof search. Moreover, since the logic VCU corresponds to the logic of comparative concept similarity, we aim at comparing the performances of ToClever with those of CILC, a theorem prover for this logic. Thank you very much for your attention. Ciao a tutti gli amici del Gulp e agli amici di Rende.
Hello everybody, I'm Carlo Taticchi and I'm going to present this work on labeling semantics for weighted argumentation frameworks. I'll start introducing some background notions on argumentation theory, then I'll present our approach to a weighted labeling, and before concluding I'll also show you our work in implementation. First of all, an abstract argumentation framework is a directed graph in which nodes are called arguments and the arrows represent attack relations. The goal in this framework is to identify a subset of arguments that share some good properties. For instance, we can look for arguments that do not attack each other. Subset of these arguments are called conflict-free extensions, as the singleton A and C, or A and D together in this example. But you can use different criteria, called semantics, to obtain different subset of arguments. Unadmissible semantics, for instance, only accepts arguments that are defended. In the example, A and D represents unadmissible semantics since A is not attacked and D, that is attacked by C, is also defended by A. There are a few more of these semantics that I'm not going to discuss now because of time constraints. An alternative approach to extension-based semantics is provided by labeling functions that mark the arguments in the framework according to some kind of rules. And there exists a correspondence between extension-based and labeling-based semantics. For example, here you can see two conflict-free labelings in which if an argument is labeled in, represented in green, then it is not attacked by any other in argument. And if an argument is out, represented in red, then it must be attacked by at least some other in argument. And for what concerns the admissible labeling, if an argument is labeled in, then it is only attacked by out arguments, and the condition for out arguments stays the same as before. Finally, in a complete labeling, we also want any argument that is only attacked by out to be in. For instance, here we cannot leave the argument E undecided. It must be in. And classical frameworks can be then enriched with the additional information of how strong each attack is. And in this case, we need to reinterpret the notion of defense. For example, it seems quite reasonable to think that the argument C, that is attacking D, cannot be defended by argument A, since the attack of A toward C is of 2, while the attacks of C towards D has a strength of 4. And however, if we consider the arguments A and B together, their overall strength of 5 seems sufficient to beat the attacks of C towards D. And this is an example of what we want to obtain, there is a labeling for weighted argumentation frameworks, which allow to identify arguments accepted by the various weighted semantics. And for instance, the two labelings here correspond to two weighted admissible extensions, since the collective defense of A and B that are in arguments is sufficient to beat the attack of C towards either D or E. But D and E cannot be defended together because the attacks of C have an overall strength of 8, while the collective defense of A and B only reaches a strength of 5. And let's start looking at the weighted conflict-free labeling, and we show that actually it coincides with its non-weighted counterpart. Indeed, the notion of conflict-freeness is not affected by weights, since it only checks whether an attack exists or not between two arguments. Things are different for weighted admissible labelings, in which if an argument A is labeled in, then for each attacker B of A, say B1 in this example, the combined strength of the attacks from B towards other in arguments must not be greater than the combined strength of the attacks coming from in arguments, for instance C and D in the example, towards B. And this must be true for all the attackers of A, so it also applies to B2 in this example. And this is another example of weighted admissible labeling, in which we can see that the argument A can also be left undecided. And if we instead want a weighted complete labeling, then it is mandatory to also label the argument A as in, and indeed it is also always defended by the arguments C and D. Now I'm going to show you an implementation of the weighted labeling through the Conarg web interface. In this interface you can draw arguments and the attacks between them. Then you can select semantics and compute the corresponding labeling. To conclude, I presented labeling semantics for weighted argumentation frameworks. Actually, I only showed you 3 of them, but in the paper you can find more. And we have also seen a demonstration of how these labelings work. And for the future, we want to first of all use different notions of defense to obtain different kind of weighted labelings. And we also want to work on the undecided label. We can, for example, give explicit conditions to identify undecided arguments, and we can also differentiate this label into 2 sub-labels according to the don't care and don't know policies. And finally, we also want to investigate other weighted extensions and adapt them for the weighted labeling. This concludes my presentation, and thank you for your attention.
Hello everybody, I am Marco Gavanelli and I will talk about maximal and tractable fragments of the branching algebra. In this talk we will discuss about temporal reasoning, which is used everywhere in artificial intelligence and also in logic programming. In particular, we will work with qualitative temporal reasoning. The basic idea is that given a set of events and a set of relations that are interpreted as constraints between these events, temporal reasoning is the process that deduces the possible realizations of such events. And we will work with reasoning that is qualitative because we do not involve absolute time. If we restrict ourselves to points on a line, then the possible relations are just 3, less than, equals, or greater than. These are the basic relations, while we can have also non-basic relations that are disjunctions of the basic relations. For example, we could have a constraint saying that point P must be before or after point Q. Allen proposes to reason on intervals on the temporal line with a set of 13 basic relations that are mutually exclusive and complementary. The point and interval algebras are equipped with a set of operations over relations which satisfy the axioms of Tarski relation algebra. The most important are converse, intersection, with composition, and strong composition. And the sets closed under all these operations are called subalgebras. And given an instance of a temporal reasoning problem, we are looking for an interpretation that is a realization of the events satisfying all the constraints. And the model is a valid interpretation. So the main problem becomes the consistency problem. So given an instance of an algebra, is there a model or is it consistent? Another problem is the minimality problem. Given an instance, is every relation realizable in at least one model? These two problems are equivalent under polynomial Turing reduction and will be interested in particular in tractable fragments. After Allen defined his interval algebra, people started thinking about tractable fragments. The first was one based on convex relations. Later, the pointizable fragment was found, in which all the constraints can be defined in the points that are extremes of one interval. Then the Ordhorn fragment was found. This is the first maximal tractable subalgebra, and it is also tractable by path consistency. Many temporal logics have been extended also to deal with branching time, and also the point algebra has been extended to branching point algebra with a new possible basic relation that represents the fact that two events could be unrelated or on different branches. And also the interval algebra has been extended to branching time, and in this case we have 6 new basic relations. As an example, we could have that right after school, Bob and his friends will meet at the nearby restaurant. They'll decide whether to go to the cinema or to the theater, in which case they'll take the subway. So in this example, the activities of going to the cinema or to the theater are actually unrelated. They are on different branches. So this cannot be represented with the linear temporal algebra. Concerning tractability, of course, we have the same tractable subalgebras of the linear case, but also we can have more. The first that was identified was BA convex, that includes the convex fragment of the linear case. It is actually a weak subalgebra, and path consistency in this subalgebra provides minimal labels. And then in a recent publication, we also extended the Ordhorn subalgebra to the branching case, obtaining quite a large fragment. But we still have several open questions, like is BA Horn maximal or not? Are there any other tractable fragments? Which of them are tractable by path consistency? In 2001, Broxwell introduces the branching disjunctive point algebra, in which one can also have disjunctions between basic and also non-basic point relations. And he was able to obtain a complete classification of the tractable fragments. So there are exactly 5 maximal tractable fragments that are defined in this way. Each of the fragments contains disjunctions in which one can take exactly one element from one of these gamma sets in disjunction with as many elements as wanted from these delta sets. The algorithm he proposes has a complexity slightly worse than that of path consistency. Can we use Broxwell's result on the point algebra to derive properties on the interval algebra? 2 fragments out of 5 cannot be used because they do not have the less than relation that is intrinsic in the concept of interval. One of the fragments corresponds to BA Horn, so it is an alternative proof of the fact that BA Horn is tractable. Actually, we had proven something stronger, that is that BA Horn is tractable through path consistency. Another fragment corresponds to a new fragment, and we call it the pointizable branching interval algebra. And another one corresponds to another new fragment that we call BA Lin. Out of these fragments, which ones are tractable by path consistency? We have proven in a previous publication that BA Horn is tractable by path consistency. Instead, for the new tractable fragment BA point, we found a counterexample, so this is not tractable with path consistency. And for BA line, we still do not know. This is an open problem. In this paper, we also have maximality results. For BA horn, we have proven that it is maximally tractable. To conclude, in this paper we proved the maximality of BA horn. We found two new tractable algebras of the branching interval algebra. For BA point, we were able to prove that it is not tractable by path consistency. Still some open questions. Is BA line tractable also by path consistency? Are BA line and BA point maximal? And of course, we do not know if there are other tractable subalgebras.
Good morning. This is joint work with Valentina Liozzi and Daniele Teseider-Dupré. We study the relationships among concept-wise multi-preference semantics and self-organizing maps. The starting point is recent work on a concept-wise multi-preference semantics for rank knowledge bases in the lightweight logic EL, and where preferences are defined with respect to concepts, and they are integrated into a single preference for the evaluation of conditionals. The idea of the paper is to consider these multi-preference semantics to provide a logical interpretation to self-organizing maps, which are psychologically and biologically plausible neural networks. The idea underlying the semantics is that relative typicality of domain individuals depends on the aspects that we are considering for comparison. And so Bob may be more typical than Jim as a sport lover, but less typical than Jim as a swimmer. There are other technical motivations, the property that we require for entailment, for non-monotonic entailment, and for instance satisfaction of KLM property, of the ability to deal with specificity and irrelevance and other properties. I will not discuss this part in detail. The language extends EL, which contains strict inclusions with divisible inclusions corresponding to conditional assertion. A divisible inclusion, typical C included in D, means that normally C's are these, and this kind of extension has been considered in the description logics with different semantics. Here we consider a multi-preference one. In ranked knowledge bases, a concept like horse may have different properties, with typicality properties with different degrees, and such properties and their degrees can be used to establish a preference relation between individuals. For instance, spirit is more typical than body as a horse, as spirit has no saddle, but body has no tail, and having no tail is more serious than having no saddle. To evaluate general conditionals, as these preferences may not agree with each other, we have introduced the notion of global preference. Global preference is defined by, from the specific ones, by a modified Pareto condition, and is added in a model, in an interpretation, and it is used to evaluate the typicality of a concept. Self-organizing maps have been studied as plausible neural network models, and they learn in an unsupervised way, sometimes from few positive stimuli, and they are biologically plausible models of category formation. A self-organizing map consists in a set of neurons or units which are spatially organized in a grid. Each unit has a weight vector of the same dimensionality of input vectors, and each time, during training, each time an input stimulus, an input vector is presented to the grid, the best matching unit is selected. That is the unit which is closest to the stimulus X. Then the weights of the best matching unit and its surrounding units are updated in such a way that subsequently these units will react to the same stimuli similar to the stimulus X. And the map is organized topologically. And so the idea is that of using the notion of relative distance of a stimulus to a category, which has been introduced by Liozzi and Plunkett to evaluate a new stimulus with respect to a category. This notion of relative distance exploits the distance of a stimulus, of the new stimulus from the best matching unit of the category, and compared with the maximal distance of a known instance of a category from its best matching unit. Using this notion of relative distance, we build from the map, we build an interpretation. Categories are regarded as concept names, and the domain of the interpretation is the space of all the possible stimuli. The preference relation with respect to a concept is defined through using the relative distance of an element with respect to the concept, so that X is preferred to X prime with respect to concept Ci if the relative distance of X from Ci is less than the relative distance of X prime from Ci, and the typical elements with respect to the typical Ci elements are the best matching units of category Ci, essentially. So we define in this way a preference relation where the global preference is defined as usual, and the interpretation of concepts is defined as follows. Concept Ci contains all the domain elements whose relative distance from Ci is less than the maximal distance, relative distance of an element of Ci from the category itself. Equipped with this construction, we can evaluate conditional and strict inclusions over this model, the model of the sum, extracted from the sum by model checking, exploiting the notion of maximal relative distances from a category and the relative distance of a best matching unit of a category from another. So the verification may be not trivial, but essentially is model checking. The process of generalization can be seen as a sequence of revision steps. And of course, there is much work to conclude concerning the relation among neural network and symbolic reasoning, and our approach, our way of linking SOMs, self-organizing maps, and conditional interpretation may be exploited as a basis for an integrated use of SOMs and diffusible knowledge bases. For future work, an experimental evaluation is needed. Thank you for the attention.